let's graph some rational functions. So again, when we talk about rational functions, we're talking about fractions, functions in a fraction. And specifically, we are looking at functions today where x is in the denominator. Now, we're going to use what's called a parent function to graph rational functions today. And what a parent function is, it's the most basic version of a function without any transformations applied to it. So today's example, in these notes, we're looking at f of x equals 1 over x. That is the parent function for rational functions. Okay, we're going to graph this, and first we'll look at what this graph does when we put a few values in for x. Okay, so let's say I put the point 1 in for x. Well, that would be 1 over 1, or 1. So I'd have a point here at 1, 1. But then you can see as I put bigger and bigger numbers, like 2, it would give me 1/2. 3 would give me 1/3. If I put, let's say, 10 in, that'd be 1/10. So it's going to get smaller and smaller and smaller as I increase. 2 is about 1/2, 1/3. It just kind of approaches 0, but it's never going to touch it because even if I put a number like 1,000 in here, that's 1 over 1,000, which isn't 0, but it's close to it. Now let's say I put in smaller numbers like 1/2. Well, 1 over 1/2, it's kind of a weird fraction. This is 1 divided by 1/2, which is 1 times 2 over 1, or 2. So it kind of flips it. So 1/2 gives me 2. And likewise, 1/3 gives me 3. So 1/2 would give me 2. 1/3 would give me 3. 1,000, or 1 over 1,000 would give me 1,000. So again, it's going to approach this line without ever touching it. Let's also think about what happens if we put in some negatives. We'll make a new chart. If I put in -1, 1 over -1 is -1. So I have a point at -1, -1. And then let's try -2. That's going to be 1 over -2, or -1/2. Okay, so it looks like the same thing might happen. -3 is -1/3, and so on. So that's going to approach 0 this way without ever touching it. And if I try small negative fractions, like -1/2, that's going to flip it to -2. And so on. -1/3, -3, and it will go much the same as before. So you can see that when I graph this, there are these lines, and for the parent function, they are just the axes, the x and y axes, where the graph isn't going to touch. Now these are called asymptotes, a line which a graph approaches but doesn't touch. It's called an asymptote. So it's a value which the graph is getting closer and closer to, but it's never going to equal that number. It'll just approach it. It'll get infinitely closer and closer and closer, but no matter what number we put in, it's never going to equal that line. This function can never equal 0 for any value of x because it's not possible to put 1 over 0. And so it's an impossible value for this function, which will just approach. Now what we're going to use this parent function for is graphing with different numbers applied to it that's going to transform the graph in some way. So adding a number in the denominator will shift the graph one way. Subtracting a number will shift the graph another way. So if we add a number in the denominator, that's actually going to shift the graph left. And if we subtract a number, it will shift the graph right. And we can see this if we make a t-chart here. We won't do this for every single one, just to show an example. So before, for my graph up here, my parent function, if I put 1 in, that gave me 1. But here it's going to give me 1 over 3. So I have a point at 1 1/3. If I wanted to see where y equals 1, I would have to do -1, 1. -1 plus 2 is 1. So it is going to change my picture somewhat. I have a point here at -1 1. And 1 gives me 1/3. 0, in fact, gives me 1/2. This graph's a little too small to show this on. If I put in -2, that gives me 1 over 0. That actually is not possible. We can't divide by 0. Okay, so that's where my asymptote is. It's at -2. But as you can see from my red dots there, they are going to approach 0 much like before. So all this did was shift my picture left 2 spaces. So I can assume the rest is going to follow the same pattern as before. And I can just draw the picture that I know it's going to look like, approximately. It's okay if it's not perfect. I probably should have a point right here at -3, -1. And if I look at that, 1 over -3 plus 2 is -1. So that is where I'll have that point right there. Yes, that's kind of what my graph would look like for 1 over x plus 2. We can use a similar logic to know that when I have 1 over x minus 4, I'm going to shift my graph right 4 spaces. Right here. And to check that, if I put in 4 for x, 1 over 4 minus 4, that's 1 over 0. Can't have that. That doesn't work. We can't divide by 0. So that is why it shifts it to the right. It moves our asymptote over there. And I'm still going to have one here at y equals 0. Okay, and you can always double check these sort of anchor points, these corner points here. If I put in 5 for x, I do get 1. And if I put in 3 for x, I get -1. Okay, so that kind of confirms, again, in another way, my picture. And that's always a good idea, just to double check those values to make sure you've moved your asymptotes to the correct spot. Check those corner values, make sure that those are what you think they will be, and the rest should work. Now that's what happens if we put a number in the denominator with x, adding or subtracting. Let's see what happens if we add or subtract a number to the outside. Well, as you could probably expect based on what you hopefully know about y-intercepts, adding a number to the outside will shift our graph up or down if we subtract. And again, we can test this, but adding a number outside will shift it up, subtracting will shift it down. So what we should have on this next one is our normal asymptote here at the y-axis, and we should have our new horizontal asymptote up here, up 3 spaces. And let's check those points. Let's check these anchor points here. So if I put 1 in for x, I should get 4, and 1 over 1 plus 3 is 4. And if I put -1 in for x, I should get 2. And that makes sense because -1 plus 3 is 2. So to move the graph up or down, we add numbers or subtract them to the outside of the fraction. So here we have 1 over x minus 5. That should move it down 5 spaces. But leave the middle the same. And again, it's enough, I think, to check these corner anchor points that we know are just kind of one up from the asymptote on each side, because that's what our parent function had. So let's check these. If I put in 1 for x, 1 over 1 is 1, 1 minus 5 is negative 4, and that is where this point is. If I put in negative 1, I get negative 6, and that works out as well. And then it's just a matter of getting my graph on there. And you can just get close enough is okay. We know what's happening. Just like that. Now we can also combine and try both of those at once. So for both of these rules, we have to remember x minus 2 here in the denominator will go right 2 spaces, and plus 3 will go up 3. It's kind of the opposite inside the fraction. In the denominator, it will, if it's minus, it'll go right. If it's plus, it'll go left. It's kind of backwards. And in the outside the fraction, it will do what you expect. Positive goes up, negative goes down. So this goes right 2, so I'll have my vertical asymptote here. And up 3 means I'll have my horizontal one up here at 3. And again, check these anchor points just to make sure. So I should have a point at 3, 4. If I put 3 in for x, I get 1 in the denominator, so 1 over 1 plus 3 is 4. And if I put 1 in for x, 1 minus 2 is negative 1, and 1 over negative 1, negative 1 plus 3 is 2, which is what I have here. So that worked out. I can be confident that I put those in the right spots. Not my best curve on that one, but close enough. And let's try one more. X plus 5 in the denominator will go left 5, and minus 6 in the outside the fraction will go down 6. So I should have my vertical asymptote at negative 5, my positive one, or my horizontal one, at negative 6. Not sure why I said positive. Just like that. And again, let's check these corner points. This would be at negative 6 for x. Negative 6 plus 5 is negative 1, so I have negative 1 minus 6, which is negative 7. I believe that's where I am. Yep. Then this point is at negative 4 for x. Negative 4 plus 5 is 1, and 1 minus 6 is negative 5. And that is where I am. So all good there. We can draw our graphs approaching the dotted lines. So that is how we use a parent function to translate or move the graphs of rational functions. Now, as you may have noticed, we are just doing translations here with these numbers. We're just sliding the graph up, down, left, and right. So we're not dilating or multiplying by any numbers here. We may visit that at a later time, but for now, we are just moving up, down, left, and right.